I'll just explain one thing that I was asked yesterday on how a function can return a character array. A function, for example, called getName. It will ask the user to enter a name, the name, maybe his name, and then return it. If we say here void, okay, so getName, for example, like this one, if I say getName, and I say cout, enter your name, and then in, for example, get line name 100/n. This is just to read the name. Okay, I have here, for example, char name 100. Now, in this, you see here, I am reading the name. But now, how can this function returns the name to the caller, to another function? Maybe it was called from main or from another function. Two ways to do this. Either, for example, here, instead of having this one declared here, for example, I say here, a char name, like this, and this way, anything I read into this name, it will be returned automatically, because this is we call a character pointer. The character array is actually a character pointer, so it is not a copy of the array. It is just a pointer to where the array is stored. So anything you read, it will go back to the caller. But normally in the set and get functions that I ask you to write, normally you will not do it this way. So what you will do is you will do it this way here, okay? You will not have anything here, but you will declare it inside the function. When you declare it inside the function, you will read it. It will be stored in this character array. But this is local. This is a local array, which means it will be deleted from memory after going back from this function. After this function finishes, it will be deleted from memory. So the way to do this is you return it using a return statement. You say return name, like this. Of course, since you return something here, you have to change this one from void to the same type of name. What is the type of name? It is not char, just char, because char means one single character. So it's a character array. If you do this like this one here, you say char, then what? If you do it like this, okay, it means that this is a character array. But normally, this is not the way we do it, because it is not accepted. It's not accepted to use brackets here for the return type. So how to do it? You say star instead. So a star, char star means the same as a character array. It is a pointer. A character array by itself is a pointer. So this is a pointer. So you do just char star. Now, normally we put the star somewhere, and we don't put it in the middle. So some people, what they do, they say char star like this one, to mean that this is a character pointer. And in most, what you will see it like this one, star get name like this. Actually the star, the spaces between the star and the words here, char or get name, it is not a matter. And you can put space or not, it doesn't matter. But where to put it, some people they put it like with the char, some people they put it with the name of the function. So this is how you return a character array. How you return a character array. If you do it using string class, then you will not need this one. But for us, we already declared arrays inside classes as character arrays, not as strings. So you use it this way. Also the same way here, if you have it here, for example, if you have something here like n, this is like an array as a parameter. Instead of doing it this way, you can do it star n. You do it star n. Character array and character pointer are the same, because a character array is by itself is a pointer. So this is just to explain what is the relationship between character array and pointers. We'll go back to what we were talking about yesterday, in explaining what is recursion. Recursion means repeating. When we say recursion, means repeating the same thing. And we call a recursive function. A recursive function is the function that calls itself. In functions, you should not put a call. For example, here, I have here, for example, void print. Suppose I have something like this, and I do some code here, and then I say here, print. Don't do this. Don't do this. If you do this, it means that function will call itself. It is like infinite loop. It will not stop. It will not stop. It will become very crazy. It will become very crazy, and your computer you have to shut down your computer. You cannot do anything, because it will take too much resources out of this. Okay? So don't do this. But for us, we will do it. But because we know what we are doing, I'll tell you, you need to stop the recursion. And I'll show you how to stop the recursion. Because this is very important. In recursion, you should know how to stop the recursion. In here, there is nothing to stop it. So, don't do this. What we had before, what we have yesterday, is this how to calculate a factorial. Using normal loop. A factorial, I said, is, for example, a factorial of 5 is 5 times 4 times 3 times 2 times 1. Or you can do it the other way. 1 times 2 times 3, 4, 4, 5, up to the number. So this is what we call factorial. And I showed you yesterday how to do it using just a normal loop. Okay, how to do it using a normal loop. Now, how to do it using a recursive function. So let's say call this one fact1, and then we will have another one called long fact2, integer n. With this one, we are going to do it recursively. Means it will calculate the factorial just by calling itself several times until it finds the solution, the product. Okay, I want to get the factorial as we did yesterday, factorial of 5. What is the factorial of 5? 5 times 4 times 3 times 1. Okay? This is the definition of the factorial. You start from the number and multiply by the next small number, then until you reach 1. Until you reach 1. So, what is this one here? What is this one? We know factorial of 5 is 5 times this. What is this? Huh? In terms of factorial, can you see here? What is this? Huh? Of what? This is the factorial of 4. You see? This is the factorial of 4. So instead of, okay, so what, for example, I ask this function here, fact2, I'll ask it to give me the factorial, for example, of 5. What it will tell me, it will say, or I'll ask someone, one of you. You say, for example, I ask you, I'll tell you, give me the factorial of 5. You'll say that, well, I know it is 5 times the factorial of 4. Go find someone else who knows factorial of 4. So I'll go, what is the factorial of 4? They'll say, it is 4 times factorial of 3. Go find someone to tell you what's the factorial of 3. So like this. Okay, so instead it will be like factorial of 4, like this. Then what is the factorial of 4? It is 4 times factorial of 3. Factorial of 3 is 3 times factorial of 2. Factorial of 2 is 2 times factorial of 1. Okay? Factorial of factorial of 1 is what? 1 times factorial of what? Can we continue? Huh? Now, should we continue? It is 1 times factorial of 0 and then 0 factorial of that. Can we continue this way? No. Because we have to stop. In recursion, there should be what we call a base step. This is the step that will stop the recursion. At this moment, you should not go back and do it recursively. By definition, in mathematics, a factorial of 1 is what? Is 1. This is by definition of math, not from us. They say a factorial of 1 is 1. A factorial of 1 is 1. Okay, now, so you see here, in this one, actually we are repeating. So, again, until we reach this one, this is we call the base step. At this moment, we stop recursion. Okay, so how to do this one in the function? So this is what I have here. Okay, so the first thing you do is the base step. This is very important. So I need to do the base step. This is where you stop recursion. Stop recursion. How to stop it? We just, if n equals 1, what is the factorial of 1? Huh? 1. So what we do is we return 1. Okay, so this is simple. If it is 1, I'll say, oh, it is very easy, just 1. And I'll not do anything. Now, this is the base step. We need to do the recursive step. So here, either you say else, or you don't need to do it, use else. Because if you go inside this one, it will go back from the function. So you can do it with else or without else. So let's say here, better to use, or more clear to use else. Else. Now, else we don't know what is value of n. It is 2, it is 10, it is 1 million, we don't know. What we know, that of any number, the factorial of any number is what? It is the number times the factorial that one was before it, the number that is before it. Okay, so I tell them, okay, I know it is, for example, what's the factorial of 100? I know it is 100, but multiplied by the factorial of 99. I don't know what's the factorial of 99. Go to find someone to tell you. Okay, so this is what we will do. Okay, here it is just n multiplied by fact 2, because we call it, let's change it so you'll not get confused, and we'll make it fact, just fact here, because we already changed that one to fact 1. So it is just fact of what? N minus 1. Finish. So you say if it is 1, it is, if you want the factorial of 1, just return. No, sorry. Sorry, I should have it return. Okay, sorry. Okay, so return means to answer the one that asks you, whether it is a function or someone asks you. So you tell him that factorial of n, the number that he gave you, is this number multiplied by the factorial that is 1 less than this number. This is what we call recursive function. We call it recursive function because it will call itself several times. It will call itself several times until it reaches 1. Until it reaches 1. Any question about this? I'll show you other examples and how to do, but for this one, do you understand it now? Because we start with factorial, because factorial normally is an easy example, an easy example, so you can understand what we mean by recursion. I'll show you another example. It might be a little bit confusing, but it is the same concept. Okay, yes?
The number will stay the same.
Huh? Yeah. How will it come back? Okay, so what will happen? What happens in recursion? What happens in recursion? Suppose I have here, this is a function called for factorial for fact. It will call this function here. So what we'll do, we'll trace it. We'll use the debugger to trace it. So here in debug, okay, now it is on this step. I want to go inside, so I press F11. Now I am inside the factorial. Here in the down, I'm not sure if you will see it, it will tell you what the values of the variables, the local variables and the global variables. We have a local variable n. So the value of n now is 5 because we call the function with this one. So we go here, if n equals 1, no, it is not 1. So we will not go to this one. We will go to, okay, to this statement. This statement says to return a value, but the value is not yet ready. The value to be returned is not yet ready. It is n multiplied by something, but that something is not, we don't have it. It depends on another call to the function. So if we say here F11, we will go back to the function, you see? And now you see n is 4. Now n is 4. And then again, we'll go to this one. We press again F11 and it will call the function again. Now n is 3. Huh? Because we called the function with n minus 1. So you get 5. You send to the function to call the function with that 5 minus 1, which is 4. That's why we call it with a number that's less by the previous one. Otherwise, you will not stop. If it doesn't decrease or increase, it will not stop. If it doesn't change. Okay, so now we go again. We'll continue this one. And F11. Now it is 2. Okay, you see here it is not going to the base step. So now we'll go here again, and again now it is 1. So now it will have an answer. What is the answer? This is when it will return 1, it is because it was called before with n equals 2. And fact n minus 1, which is 2 minus 1, which is 1. So now we will have an answer for fact 1. Fact 1 is 1. So that's why it will go back to this statement. It will go to this statement and it will return a value. Okay, so you see here, we'll go here, it will come to this statement. Now when we execute this statement, it will go back to this statement here. Because now it has an answer, it is 1. It will return 1 and it will multiply it by 2. Now this one, it will return 1. You see here, look at it, when I press F10 here, it will go to the end of the function. Means this function call finishes. Now, how many calls? We still have 5 or 4 calls before to the same function. So it will go back to the previous call. Okay, so now F10 here, it will come back to this one. What is the value of n now? What is the value of n? 2, because this was the previous call. It went back to the previous call, to the previous step. What was returned? 1. So it will multiply 2 by the value of this function, which is 1, and it will return it to the one before. Okay, so I'll press here. Now it will not call the function again, it will just return the value. Okay, so you see here, it will come back to this one. What is the value? It is 2. What's the value of n? Is 3. Again, now this one, 2 times 3 is 6. 2 times 3 is 6. So it is the same as what we had before here. 2 times. So now it is, n is 3, it was 3, and 2 factorial is 6. So now it will go back to this one. It will go back to this one. F10. Now it will go, this is, so it was 5 times factorial of, 4 times factorial of 3, which is 6. That's why the value, it was 24. So now it is going to this one here. The factorial of 4. Now the value is n. This is what we are left with. When we press here, it will have an answer to what? To main. It was called from main. So it will come back to here. It will come back to here. So press F10, it finishes, then it will go back to here, to main. So it will backtracking, that's the term that I was looking. It's called backtracking. It will backtrack to the previous calls. And it will give you the answer, which is 120. So the answer is here, as you see, 120 here. Okay, anyhow. So, you understand this, how it is doing it? Now I'll show you another one. So you might, if you want to understand it more, there is something called, we use it also, this one, as an example of, to demonstrate recursion. Something called Fibonacci series. Something we call it Fibonacci series. And this is also in mathematics. Series means numbers that take some type of sequence. It's not just like by increment of 1 or decrement of 1, sometimes by steps. But it will be normal. So what is, for example, Fibo, let's say Fibo of, what are the series? First, I'll show you the series. The series start with 0 first. It will be 0, the first. Then 1. Then here, the Fibonacci series, any number, any Fibonacci number, the value of that number is the sum of the 2 previous numbers. So now we are in the 3rd number here. For example, here, let's say here, I'll show you the sequence here. So this is number 1. This is 2, 3, 4, 5. This is what we call Fibonacci numbers. The numbers itself, the positions of these numbers. The first one by definition is 0. This is in mathematics. The second one is 1. The third one is we start the sum. So the third one is the sum of the two previous. What was the two previous ones? 0 plus 1, which is 1. Okay, now, what is the two previous? 1 plus 1 is 2. Now, this one, 2 plus 1 is 3. This one, 5. Huh? Okay, then if we continue, for example, this one will be what? So this will be 8. Then, okay, now number 8, it will be 13. Because 5, and you continue this way. And you can go to any number. So if you ask someone, I will ask, we'll do the same as with the factorial. I will ask someone, give me what is the Fibonacci number in position 9? But can you understand it this way? Let's say here, for example, I say, what is the Fibonacci Fibo of 9? So you will say what? It is Fibonacci of 8 plus Fibonacci of 7. Okay. And they say that I learned this one in mathematics. But what is Fibo of 7 and 8? I don't know. So I need to now to ask how many people? Now I need to ask 2. Not just one like factorial. Now I need to ask 2. I'll ask someone to give me the factorial of 8. Okay, so I need the factorial of 8 equals Fibo of 7 plus Fibo of 6. And Fibo of 7 equals Fibo of 6 plus Fibo of 5. And we continue until we reach what? We continue this one until we reach Fibo of 1. What is the Fibonacci of 1? In the series here, what is by definition? Huh? It is 0. Okay, so Fibo of 1, Fibo of 2, Fibo of 2 is 1. Fibo of 1 is 0. This is by definition, by mathematical definition. Huh? So now, you see here we start, for example, from 9. So it will go to 8 and 7. 8 will go to, so you have another 3 here, another 3 here, and this we build here another 3. So you see here the tree becomes bigger and bigger and bigger and bigger and bigger, because now we are doing it twice. We are calling the same function twice, not just one time. Here, if we will do it, for example here, so we say long Fibo, integer n, we want to get the Fibonacci number at position n. So first we start with the base step. So we need to write the base step. This is where we stop. What is the base step here? If it is 1, I think here they start, I think, from 0. Yes, I think they start from 0 or position. Whatever, I think it will not Anyhow, it will not put. Let's say here, put it as 1 and 0, so it will not be confused, because normally it is a positive number. For factorial and Fibonacci, it should be a positive number. So 0 is a positive number. Also for factorial, by definition, it is also 0. Factorial of 0 is 1. So here you can say if n equals 0, or where is it, this one? Or n equals 1, we return. So this one. So in here, the best step what will be, if n equals 0 or n equals 1, what we return? What we return here? This is n. This is here n. Okay, this is n. And this is the Fibo. Okay, this is the Fibo, this is n, and this is the Fibo. So if n is 0 or 1, what we return? We return what? N. It is the same as n. If it is 0, it is 0. If it is 1, it is 1. So if it is 0 or 1, we return what? Just n. So here we return n. Else what do we return? You see here what we are returning. This is n. So what is this in reference to n? N minus 1. And this one? N minus 2. So I'll say here, just return Fibo of n minus 1 plus Fibo of n minus 2. Okay? So this is the recursion. But if we trace it, we'll go here. Wait, it will be so confusing, yani. These are just examples. They are considered simple examples. They are not that complicated because you can understand it and you can trace it. But there is something about recursion, that recursion consumes too much memory and slows down the program. Consumes too much memory, because later on, I think if you'll take data structures, you'll understand this one, because I don't want to go and explain it. There's something called stack, and it will just put things in that stack and then take it out. So we say push, pop, push, pop, push, pop. And this takes too much memory and also slows down the program. So if you can do it directly without recursion, it is better. But sometimes there are problems that is difficult to do without recursion. Difficult either to write the code or to understand it. I have here what I told you about yesterday, the towers of Hanoi. Okay, towers of Hanoi. Here it's already here, and I'll show you how you can play. Okay. This one here with three discs. Now I have 3 discs here. And I am moving from this position, this node here or road here to this one. And I can put something in between. So I told you yesterday, the rule to play this one is that you need to move only one disc at a time. And you cannot put bigger disk on smaller disk. You can put small disk on top of bigger one, but not the opposite. So here, and they are first in sequence. The smallest in the top, then little bit larger, until the end of here. So how to move? I take, for example, this one. I can put it either here or here, whatever. Let's say I put it here. Then this one, can I put it here? You cannot. It will go back. You cannot put it on top of smaller one. So I can put it where? I can go here. Then what to do? Can I put this one here? I cannot put this one here. I cannot put this one here. So what to do? I can put here, this one. Go back. Huh? This one? Put it here. Okay, put this one here. You see? Then I move this one here. Okay, then in here or in here? Here? In the middle? In the first, okay. Then this one in the middle. Then I cannot put this one in here. Well, you see here, we are not going to continue. So better to use this one put here, this one put here. No, this was before here. Okay? Or this one here, this one in here, then in here, then in here, then we put this one here, then we put this one here, then we put this one here. Okay? But it took 17 moves. Actually, it is just 7. The actual one is just 7. Okay, so this is how what is that? What they call, this is mathematical problem in computer science. If you calculate, I tried to calculate how many seconds it will take you for, because you will need 2 to the power of n. N means how many disks you have. With 64 disks as the original problem, you will need about, I think, 300 or billion years. About 300 billion, not million, billion years to do this one. So it's not, it will grow too much. So for example here, now if you can start with some other numbers, and here I'll show you. This is a program, a recursive program. You don't need to write it or something, but just I'll show you that it is easy to solve this one with recursion. Okay, so we are moving from road to road. This is how many disks we need. So this is how it is doing it. We have the base step here. We have the base step here. And it is calling itself twice, 2 times. It is calling itself 2 times. It is a simple function. It is not confusing one. It is not confusing one. It is calling from road here. We start from this one. You see here, this is like A, this is B. Okay, so, and it is not a complicated one. Not a complicated one. But I'll show you the opposite, the other one. So here, if we if we try it, for example, this one, if we try it with 3 numbers, for example, 3 disks, okay, it will tell you like this one here. It will tell you first move disk 1 from road A to C, then 2 from A to B, then 1 from C to B. Then how many steps? 7 steps only. 7 steps only. But let's try it. For example, here with 5. Let's say I have 5 disks. You see here how many? 31 steps. For 5 it is 31 steps. What if we have, let's say, 10? 2 to the 10, you know what is 2 to the 10? 2 to power of 10? It is 1024. They say grows exponentially. It's exponentially, so it expands like explosive recursion. Right, but it takes too much. You see here 10,023. Actually, it is 10,024 and minus 1. Because we had that one for 7 steps, 2 to the 3 minus 1. So this is 1023. But if you try other numbers, bigger numbers, and it will be 2. Here you can use the timing for, as we did yesterday. You can time it, how much it will take. For 5, 6, no problem. But later on, if you go to 10, 11, 12, it will start slowing. It will, if you say 20, you go home, have lunch, come back, you will see it is still running. Because it is not. But don't try it with 64. Otherwise, it will not, never it will stop. I think it will not, in your life. Any question about recursion? Any question about recursion? No, it is increasing the time of the program. It takes too much time and too much memory. Yes. You see here, because I didn't want to go into this one before, so because it will be a little bit confusing, but you see how many here, how many parameters we have? We have 1, 2, 3, 4. This is integer, 4 bytes. This is 1, this is 1, this is 1. So we have total of 7 bytes. 7 bytes. Inside the program, when we call a function, you see here in the program, the execution of the program will go in sequence. You talk in algorithm, what we call sequence structure. Then it will go step by step. But if you go in, if you call a function, it will leave this position and it will go to that function. Later on, it has to come back to it. So how to know where it was before? It has to save its position, and also the value of all other local variables. How to save it? It will push it in a stack. You know a stack, when you go to the restaurant, you have those plates. You know, you see the plates? They put the plates like this. So the first plate they put it like this. Then the second plate will be on top of it. Third, fourth, fifth, sixth. Okay? Then when you take one plate, from where you take it? You take the first or the one on the top? Huh? I have here, this is like I have here, these are plates. Like I have these papers, these are the plates. So I have 1, 2, 3, 4, 5. Now if I want to take, you see here it is put like this. If I want to take the plate, I take the one in the bottom? No, I take the one in the top. So I say pop. This is push, push, push. What you push means you are storing, you are taking memory, you are consuming memory. Here we have 7 bytes. We have to store all these local variables inside the program, inside the stack. So for each call, we will consume 7 bytes plus the previous where the pointer where the program was, which is about, also I think that one is about 8 bytes. So you see here 15 bytes. When for every call, so it will push, 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 push. So how many we have? How many steps we have? 10,023. In 10,023 steps, how many calls it did? And how many bytes it did? So that's why pushing and popping takes time also from the program. That's why they say it is slower and also consumes memory. Okay. Here, just for your reference, please look here. Please look here. You see here what is the code for this one? It is just a simple code. These lines, the C out here is not important, and it is just these 4 lines or 5 lines to solve this problem. But I have here the non-recursive version of this program. Okay, the non-recursive. So you will see here, this is, of course, I cannot remember and I cannot write it myself, because this is so confusing. Okay, so here you see how many lines we have. 100, where is it? I think I can show the lines somewhere. 154 lines. 154 lines. And if you go through it, it will be so confusing. It is not easy to understand because it is using, you see here, it is creating a stack. So it is manually, it is doing it. It's not, Recursion will do the stack in the program itself. Here it is doing it by itself. And it will do like a push and pop by itself. So here, okay, where is it? Push. Here we have push. Here we have pop. And okay, and then it starts moving the disk. So it is too much code here, too much code. If you can trace it, then you can get this from the internet if you are interested in how. This is why we sometimes use Recursion. Recursion is very beneficial for programmers to shorten the code and to make it easy. Okay, so I think this one is enough for Recursion. What we will start from now on, we're still in classes, using classes, but this is another topic in object orientation, and it is the most important topic, the most popular topic, and the most important topic. It is called inheritance. What is inheritance? Inheritance, yes, to inherit from someone. If someone dies, then the children or the wife or the husband or the relatives in Islam, we inherit with some percentage, and it is known and calculated and things like this. Is what we call inheritance in Islam. But what is inheritance in C++? What is inheritance in C++? You see here, inheritance, as we understand it, is that we get something from the parent. For example, a child, if the parent dies, the child will get something, some money, maybe a house, maybe other things. Okay? But that one if the parent dies. But here you have both, the parent and the child. You can have them both living, and still the child will inherit from the parent. So let's just give you an example of how we do this one. I'll just delete this. Suppose I have here a class. I say class. Okay, I'll say class, for example, shape. Or let's start with something simple, point. This you will see it in the presentation, so I can use it here so you will understand what is there. What is a point in mathematics? How we define a point? If we say a point in mathematics, does a point has any information? If I put a point here or a point here, what is the difference? Is there a difference between this one and this one? What is the difference? They differ in what? Coordinates, the position where they lie. How to know the point, where the point is? How we specify the point? By what? By what we call them? The x and the y, the x coordinate and the y coordinate, where it is there, where the point is. So every point has what you say here. I say private integer x and integer y. This is, every point will have a position, and we can initialize it. We say here public, and then we initialize it with certain x, certain y, and we can say also void print. So this will what we will have here. This is the class. This is the point. Now, if we go to another shape, this is a point. What if we take a circle? What if we take a circle? How we define a circle? No, a circle. How we define it? By what? How we specify a circle? Any circle. By its what? First, what is inside? What is in the middle? No, the mode in the middle is what we call the center. The center. We need to know the center. And we need also to know the radius. What is a center? Center is what? Is x and y. Is x and y. So let's write here again another class. We call it class circle, and a A circle will have integer x, integer y, and integer what? Radius. Three things, a circle. Also for the constructor, so for the constructor, a circle, we need to give it the three things: integer x, integer y, integer r, radius or radius like this, okay? And then print, void print. So now we have two classes that are separate. They have no link. You see here, we have things that are we are repeating the same thing here and here. We have the print, we have the x and y, and we have here the only difference is the radius. The only difference is the radius. So with inheritance, what do we say? We can change this one. For in inheritance, we can say colon like this one, and I say public point okay, and then this is how we do inheritance. How we do inheritance. We take this class that we want to create, and we take this other class that we want to inherit from. We just say colon, public, and the class we want to inherit from. There are names for this class and this class. We use some terms for them. We call them some. This is we call this one, the original one here, we call it the base class. So this is we call it base class. And this one we call it the derived class. That one, the base, the original one, the one that we inherit from, is the base. So point is the base, circle is the derived class. Also we call it, sometimes we call this one parent. The base class we call it the parent, and the derived class we call it the child. Okay? These terms you will learn in database. Also, if you are, I think you are going to take database, you will hear these terms also there. Also, we call this one, the base class, we call it ancestor. ancestor. Okay? We call it ancestor, which means الأجداد, يعني those that are before us. Okay? And this one we call it descendant. Descendant. So these are terms in OOP. This is related to OOP. Inheritance. All these terms are used in OOP, in object orientation. So you need at least to understand them and then try to differentiate between what they mean. So here we call it base class or a parent or ancestor. Okay? And this is what we call the derived class. Why we derive? Because we derive this class, we create this class based on that class. So we get this class, new class, based on from that. Why it is parent and child? Because of the inheritance terminology. Why it is ancestor and descendant? Because normally this one goes before. And this is how we do inheritance. But what happened? Now I did this one. Just what I did is colon, public, and then point. But inside the program, what happened? Too many things happened now. Too many things. Now, inheritance, we say that the child will get from the parent. In here, they will get everything. A child will get everything from the parent. Okay? So, what is in here? In terms of data members, we have XY. We have XY. We don't have here XY. Actually, it is there because we inherit it. We got it from point. If I go here, for example, here, let's say here, I go into print. I write the code here, so we don't want to waste time doing it the other way. Okay, so I'll say here, C out. Let's say X, Y. We'll do it in a simple way. Now, we go into here, print. We say C out, X, Y, radius. You see here, I got the error, but I'll explain to you why I got the error. I can here inside this one refer to X and Y. And I can also call any of these functions here that are there. Any function. Why I got this error? Because when someone inherits from a child inherits from a parent, does the child inherit everything? Does the child inherit the father's weight, the father's color, the father's height or something? Normally no. They inherit what is allowed. Anything that is allowed to be inherited, they can inherit. Those things that are not allowed will not be, So in point, what are X and Y? defined as what? Private. It means children cannot inherit it. Okay? But we want the child to inherit. We can, if we put it public, if I change it to public, then it means anyone can inherit. Not just the child, anyone, any person. Yani anyone. But we don't want this one. We want only those that can inherit. We don't other people to take these things. So we have private, public, and for inheritance we have something else. We call it protected. Protected means only for the family. If this belongs to the family, no problem, they can see it. If they don't belong to the family, they cannot see it. A child belongs to the family, so they can see it. Who also can see things that belong to the family, other than children? Other than that are there in the house, let's say. Other than there in the house, who else? Anyone can get inside the house? No, only the family, plus other people that are allowed. Who are those that are allowed? Huh? Friends. If they are friends to the family, they can go inside, no problem. They can get inside and think. So we have friends in C++ also. Friends will get, they will not inherit, but they can look. Friends will not inherit. They can look. They can see. And later on we'll see. So this is just you see here now. I'm not sure this one is supposed to take that. And the X out. Because now we can, since it is protected, it means that we can look at it. For those that are descendants from that, you see here, it goes now. Because it was before. So a child can see protected things from, but it is protecting from outside, not from the family. And I'll explain other things later, inshallah, in next time. So this is just to give you an idea. We might spend many lectures in inheritance to give you examples of how to use it and what we mean by this one and this one and this one. Okay, this is just to give you examples of the terms that we use, how we do it in C++, and inshallah I'll explain other things later on. Any question? This inheritance is a big topic, and it is as I told you, it is the most important topic in object orientation. In all languages that are supporting object orientation, they should support inheritance. Otherwise, they are not object-oriented languages. Because this is the most important thing. Any question about this? Inshallah, you will see more and more and more about it. Because this is just the beginning. Okay, so I think it is enough for today, inshallah, and we'll see you next week.